first activity is entitled Similar Signs. It's based on something I did many years ago on some very old geometry software, and it comes about because students really didn't understand what sine, cosine and tangent were all about, or as some students used to call it, sin, which annoys me, but never mind. That's just one of my pet hates. And they just treated sine as some magical mystery number that popped out of the calculator and really had no meaning. Now, I don't know the age of our listeners, but for some of you, you may remember trig tables, the silver books as they were back then. Russell, were they silver in your day?
Kay and Levy.
Oh, there we go. He even knows the name of them. That's pretty scary. So we used to have to look up the angles and you'd get the ratio back, or you'd have the inverse trig tables, or you'd look the tables up backwards. And that's essentially where the concept for this came from. It seems a little backward that we're using technology to take a step back to trig tables, but that's how it worked. And my students said that they understood it a lot better when they did it. So this activity can be downloaded from our website. It's called Similar Signs. There's another one for cosine, and we're going to have a look at that activity, and then Russell's got some material that he's going to share as well. Now these activities address, this one's been altered slightly since I first started teaching it this way, to address specifically the national curriculum. And the national curriculum refers to the fact that the students need to be able to use similar triangles as well. So what we've got is a triangle which is kind of dynamic because of these sliders at the top, and I've referred to it as grow, and then there's an angle alpha, and we can see the side lengths of the triangle. Now if I change this grow thing back, you'll see that all it's doing is shrinking the size of that overlaid or dotted triangle. So if I reduce it back, I can make it smaller than the original or exactly the same size. Now, I haven't made this with the intention of students changing these values in any way. It's there to actually construct, believe it or not, a table of values. Now, to start off with, I'm going to look at the angle 30 degrees, and the little anecdotal story that goes along behind that is I had students draw triangles in their books, and I told them that it had to be a right-angled triangle and it needed to include the angle of 30 degrees, and then they measured the side lengths of the triangle, and then I told them, divide this one by this one and see what you get, which of course was the opposite and the hypotenuse. And the first student answered they got something that was pretty close to a half, and another student got it, and that was close to a half. And then I said to them, well, how is that possible that both of you are getting a fraction that's about a half? Because surely your triangles are different sizes. And they said that they were. And I decided to ask a couple of, and then before I knew it, all the students were saying our ratio's a half as well. They don't always use the word ratio, or our fraction is a half. So what happens is I can then increase the size of this triangle and use it to demonstrate to students that the ratio is always a half regardless of the size of the triangle. Now for those advanced users, you know that you could actually capture this information and automatically drop it in a spreadsheet using a data capture facility. Whilst the technology can do that, it's not what I want it to do. I don't want it to calculate the ratio automatically, because there is a level of learning that takes place when the students write that information down. I want them to start looking for the patterns. But the first pattern they see is that it doesn't matter what size I make this triangle, the ratio always ends up being a half. So 12 over 24 is still a half. However, if I change the size of the angle, the ratio is no longer a half. So the students are copying down these measurements, the AC and the BC, and they just do one divided by another, the opposite over hypotenuse, and record the results. Now, just to demonstrate that you could do that calculation live on the page, I'm going to add some text, and this is a little trick that not many people are aware of. So if I type in opposite divided by hypotenuse, it writes it as though it would a fraction, and then if I right click on that measurement, or that text rather, and the students do that by control, using the control key on their keyboard, and I can hit calculate, and it wants to know where's my hypotenuse. Well, that's our longest side, that's this one over here. Oops, my mouse is wandering. And then it says, well, where's your opposite side? Well, here it is here. And I can click on that one, and it leaves me with the ratio. Then I can show that that ratio stays constant regardless of the size of the triangle, and that ratio is absolutely dependent on the angle. Not the size of the triangle, just the angle. And this is one of the national curriculum assessment tasks that we have on our website, and it focuses on specific areas of the national curriculum. Now, when students did this, and this was the interesting outcome, because some teachers say, oh look, I'd rather than just do a table of values, or I'd rather use a sign key. The interesting part is when the students recorded their sign tables, and for those people that can remember the original trig tables, they did angles to like the nearest tenth of a degree. I get the students, as the activity goes through, I get the students to go through approximately every 5 degrees, and then they estimate ratios in between those. And then they can populate their table of values just in increments of 5 degrees. That's enough. The interesting part of the story is that when it came time to the test, the students knew about the sine, cosine, tan buttons on their calculator, but most students want to know, can we still use our tables in the test? A level of irony there, when they have a very sophisticated calculator sitting in front of them, they'd prefer to use the table of values. Some students said, I'm okay if I've just got to press sine, but I don't get when I need to go backwards on the calculator, but I can look the tables up backwards. So they knew that if they started with a ratio, they'd end up with an angle. And these are the things, the concepts that are important to them. Now, the last bit of this story goes on that I had some students didn't want to use the technology to draw the triangles. That's why I've drawn them in the activity. But when I said to them, that's fine, you can use a pen and paper, within 5 minutes, those students wanted to use the dynamic geometry because it was much faster and more accurate. And they weren't too good with the pen and paper construction, whereas on the software, they were much quicker. So that gives you an idea of the sorts of things we can do. Now, while the students are doing this, they can still use a calculator. There's a calculator space in here. You can see that we can calculate values in here. So you're not restricted just to using these pages. It's not like an applet that you'd find on a web where you can only do the stuff that's on that applet. You can keep on adding a spreadsheet. You can add a graph if you want and graph the table of values. But that's how I introduced my students to sine. In fact, when I first did it, I didn't even tell them this was sine. They just wrote up the ratios, and interestingly enough, they came up with other ones, such as hypotenuse on opposite. So they were getting into things like cosec, sec, and cot. I just didn't tell them about that specifically. So that's our first activity.